Hi everyone, and welcome to a talk about our new project, What If. The paper itself is titled Automating and Optimizing Data-Centric What If Analyses and Native Machine Learning Pipelines. My name is Stefan Grafberger, and this project is joint work with Paul Gross and Sebastian Schelter. First, let's talk about ML pipelines, what they look like in the real world. If you look at the box on the right, see this part we call the last mile of end-to-end machine learning. This is the part where ML model gets trained and evaluated. Typically, this box is what a lot of ML research focuses on, and they kind of ignore the data preparation. While model training is only a small part of the overall pipeline. We look at the left, see what happens in ML pipeline before that step. First, we have data from typically several heterogeneous data sources, can be, for example, data lakes, log files, crawls, and APIs. Then we have some data preparation stages. We need to integrate and clean the data, turn the relational data into matrix data, can then be fed into ML model. And then finally, we can train the ML model. Importantly, there are many problems that can occur in these pipelines, not just during model training, but also before that. For example, fairness problems or data quality issues. But addressing these issues can be pretty difficult to do in practice because these pipelines are usually glued together using a lot of different frameworks, as you can see in the bottom of the slide. ML pipelines are often brittle with regards to the input data. Before deploying a ML pipeline in production, data scientists are interested in a variety of topics like how robust is the ML pipeline to data quality issues or maybe the fairness of the pipeline. There's a lot of research on this topic, proposing different methods to deal with these data and pre-processing related issues. On the right, we provide a few examples. Here, we collectively refer to these methods as what-if analyses, because all of these techniques ask questions like, what if there are data quality problems? Or what if I use different pre-processing? One problem now is that data scientists are interested in these questions at the moment. They have to implement these analyses manually. So we have all of these highly educated data scientists, for example, with PhDs in statistics, which are forced to spend like 80% of their time on data preparation tasks, like data cleaning, which is a giant waste of resources. This is something we want to help with by automating parts of this process. First, let's look at an example of such a what-if analysis that data scientists might be interested in. So here we have a pipeline from the healthcare domain on the right. It consumes patient data and tries to predict patients with a high chance of medical complications. We can see some data integration code with pandas. We see some neural network with Keras, and then we see some scikit-learn featureization. Now, given this pipeline, the data scientists might suddenly discover that there are a lot of outliers in the column containing the patient weight. Sometimes it is 0, and sometimes it is orders of magnitude higher than it should be. In closer investigation, the data scientist discovers that this is because of some online form that some patients fill out incorrectly. Now, the data scientists want to try out different ways to deal with this error. They could try filtering out erroneous samples. They could replace them with some default value. They could try using a different model or some different featureization. The naive way to do this analysis would be to just repeatedly make a small change to the original pipeline, execute each of these 4 pipeline variants, and look at the resulting pipeline scores. Note that this is a lot of implementation work and there's also a lot of runtime overhead because of the repeated execution of the pipeline. Ideally, we want a simple and declarative interface to specify what-if analysis. To just take the existing source code of the user's ML pipeline without requiring modifications and a specification of the what-if analysis they're interested in. And it should just automatically generate the variants of interest for the configured analysis and then optimize the execution of the pipeline variant to avoid runtime overhead because of repeated work. And this is exactly what ML what-if does. On the right, you can see how ML what-if works from a user perspective. Users just import some existing what-if analyses, briefly configure them, and then they can apply it to their own existing pipeline code with a single command. In this example, we use 2 what-if analyses to generate exactly the variants of interest for our running example. Note that ML what-if really just takes the path to the existing Python or Jupyter notebook file as input. And this works as long as the pipeline is implemented declaratively using popular libraries like pandas, scikit-learn, and Keras, so you can understand the semantics of operations in the pipeline. Now let's see step by step how ML what-if executes this running example. first, the data scientist provides the unmodified source code to the ML pipeline, and then a declarative specification of the what-if analyses. Next, ML what-if extracts a data flow plan from the user code. Here we see some relational preprocessing operations, and then estimator transformer operators that work with matrix data. Then we see these 4 different variants that we also saw in the slide earlier. Here they are expressed with something called pipeline patches, which describe a small change to the original data flow plan. And if we apply them to the original data flow plan, we get the variants that the user is interested in. We now combine these ML what-if now combines these 4 different variants into one combined execution plan. You can see that some nodes are black here. This is shared work between different variants. But then we still compute the scores for all of the 4 different variants the user was interested in and do some multi-query optimization. And finally, ML what-if reports generates a report for the data scientist, which they can then use to make an informed decision on how to change their pipeline to make it more robust. And the running example fully works, but what's maybe more interesting are what-if analyses other researchers propose in existing papers. Selected several existing techniques and integrated them with ML what-if. To make implementing new what-if analyses easy, we use an abstraction we call pipeline patches to express each analysis. They describe small changes to the execution plan and can add, remove, or replace pipeline operators. The operators they introduce use UDFs to support a wide range of use cases. For the moment, ML what-if supports 3 types of pipeline patches: data patches, operator patches, and model patches. Let's go over the examples here and see how it works. So if we want to test the robustness of our ML pipeline against data errors, some patches to insert operators that add artificial data quality errors are enough. If we want to test the impact of pre-processing operations, we can simply try removing the operator or replacing it with a default to see what happens. If we want to clean data, we can add operators that filter or fix data quality problems, or wrap the model with label cleaning code. If we're interested in the importance of a specific feature, we can just randomly shuffle all the data in the respective column on the test side and then see what happens. Of course, there are many more what-if analyses that are expressible with pipeline patches. This is just a selection of techniques that we actually implemented for our paper. As you saw in the running example with the 4 variants, there's a lot of repeated work between them. So our goal is to merge all variants into one combined execution plan that reuses as much work as possible. In general, multi-query optimization is a very difficult problem, but here the problem is much easier. Prior to execution of any variant, we already know the full workload we want to execute. The different pipeline variants are all very similar. There are only small differences between them, which are expressed with these pipeline patches. So what we conceptually try to do is rewriting the variants to share as much work as possible between them. We force specialized optimization rules and use cost-based heuristics to decide when to apply them. Let's look at 2 examples. So first, we see a relatively simple optimization rule to get started. So at the top, we see what maybe the status before optimization, and then at the bottom, after optimization. At the top, see that we have 2 different variants, one with a data projection patch on the left, and then with a model patch on the right. See that we can reuse 4 operators, but not more, because of the data projection patches on the left side. But at the bottom, we can see that we can push them up to reduce more work between the 2 variants. So here we want to push the projection up. In traditional query optimization, we want to push them down. But here the goal is to really reuse as much work as possible between variants. Second, I want to show you an optimization rule that's maybe more specific to our use cases. What-if analyses, like the one to measure the robustness of an ML pipeline, use UDFs to test the robustness against data quality errors of interest. Can be pretty expensive, for example, when you have a UDF to introduce artificial typos in a string column. At the left, we see the plan before optimization and right after optimization. On the left, we again have 2 variants, both with data protection patches. In one, we corrupt 50% of values in some string column. On the right, corrupt 100% of values. We execute this naively. We apply the expensive UDF to 150% of values. But our optimization allows us to just corrupt 100% of the data once, and then we can just sample from this fully corrupted data to generate the variance we're interested in. Now on to some highlights from our evaluation. On the left, we compare the performance of ML what-if against manually implemented what-if analyses, which is what data scientists do right now. See that ML what-if is much faster than naive implementation of these analyses. The runtimes here are just some examples. Some what-if analyses can also run for hours or days. And of course, experienced data scientists will identify some of the short work between pipeline variants, might implement some optimizations themselves, like only loading the data from disk once. You can also see how the runtime decreases with more and more manual optimizations. But without getting into really tedious, very fine-grained optimization, it's very hard to beat ML what-if. On the right, see the speed-up ML what-if provides over naive execution of different what-if analyses applied to a large number of pipelines. On the x-axis, we see the number of variants, and on the y-axis, we see the speed-up. Speed-up has a theoretical limit because we always have to pay the cost of at least one pipeline execution, even if all variants are identical. See that we are quite close to this for most analyses. One example of an analysis where the observed speedup may be a bit smaller is data cleaning. This is because this analysis cleans the training data every time, so you need to retrain the ML model in every variant. So even if the speedup is just something like 3, makes a big difference if your analysis runs for 20 minutes or an hour. But the most important advantage of ML what-if really is the automation part. Right now, data scientists waste a lot of time by repeatedly implementing the same analyses over and over. And we free them up to use the time for something else. And if you want to know more, please take a look at the paper. And to summarize, ML what-if assists data scientists by allowing declarative what-if analysis. And it works for unmodified ML pipelines in Python, as long as they're written declaratively, popular libraries like pandas, scikit-learn, and Keras. ML what-if allows experts to write and share pipeline-independent what-if analyses. Finally, all of the code is open source and available on GitHub. And there, we also provide example notebooks for everything. And thanks